Good day, grade 11s. Welcome to this next lesson in electricity and electromagnetism. So far what we've been doing is we did electrostatics in yesterday's lesson and the lessons before that. And now what we need to be doing is we need to be looking at electromagnetism. We only touch it very basically this year, and then we move on to it more detailed next year. Okay, so what you need to know, which I'm sure you do already know, is that there are magnetic fields around any magnetic object. Okay, admittedly there's magnetic fields around a lot of things, but specifically around magnetic objects. Okay, so what's important about this is that the way that we establish the direction of a magnetic field is you place a small compass on around the area. Okay, and what happens is the small compass will point in the direction of north. Okay, all the way through. So the small compass can be used to establish the direction of a magnetic field. The direction of the magnetic field is from north to south outside the magnet and from south to north inside the magnet. So the direction of the compass is always from north to south outside and from south to north inside. Now, there is a magnetic field about a straight current carrying conductor, and this field consists of concentric circles. The way they've actually done this is quite cool, is they've actually done this type of thing. They have got a piece of wire that they've held up vertically, and they've put a piece of cardboard around it. And then in this case, what they've done is they have sprinkled some iron filings around that piece of wire, and then they took that wire and connected it to a battery and closed the switch. And what happens is you'll find concentric circles forming in the iron filings. The iron filings will actually form these concentric circles. Right. So then what happened was that someone went, well, okay, this is obviously electric current going through here, and it's causing a magnetic field. And how did they know it was a magnetic field? Well, what they did was that they actually placed magnets around it, and what they found was that the magnetic needles were actually deflected around in the direction of these circles. So therefore they could say, okay, well, this is obviously then a magnetic field, because otherwise the magnets would not be deflected, right? So there is a rule that we can use. The direction of the magnetic field about a straight conductor can be found using this same rule. Okay, what you do is you hold the conductor with your right hand. So it's called the right hand rule for a reason. It's because you're holding it with your right hand, and then your thumb must be in the direction of the conventional current. In other words, it's from the positive to the negative end of the battery, and then what will happen is the fingers will curl around in the direction of the magnetic north. Okay, so if we go back to the previous question, you can see here that this is traveling from positive to negative. So the current is going this way. So if our thumb is in that direction, our fingers are going to curl into the page. Okay, in other words, it's going to curl this way. Our fingers are going to curl this way. So you can see that that is exactly the direction of the magnetic compass needles. Okay, so this is it. So therefore we can say that the fingers curl in the direction of the magnetic field, and this is where the compass would point north. Okay, right, now we need to talk about, obviously we can't go around trying to explain that in real life when we're talking about physics and trying to draw things on pieces of paper, similar to circuit diagrams, etc. Okay, so what we do is we make it a little bit easier for ourselves, and we draw it flat as if we were looking at it from the top. So in other words, we draw this as if we were looking at it from up here. There's our eye, and there's the eyeball, and there's the eyelashes, and we're looking down at it, right? So if that's the case, then what happens is they like you to assume that like to assume that everybody knows what an arrow looks like, a proper arrow, not just like an arrow that is drawn. So you've got an arrow head and you've got the feathers at the back, okay? So what they say is if the current is coming out of the page, now imagine if you are standing over here, okay? And here's your little eye and here's your mouth. I don't know why you're smiling. There's an arrow coming towards your head. Okay, but if you had to see this arrow, okay, yeah, you are standing, and you see it coming towards you, do you agree that you're going to see just a dot? The dot's obviously going to get bigger and bigger and bigger unless you move. But so this dot here represents the current coming out of the page. Out of the page, okay? Whereas if you are standing on this side, and yeah, you have to have a much bigger smile, okay, do you see that you would see the back of the arrow? And the back of the arrow looks like a cross because of the feathers. So this is the current going into the page. It's going away from us, okay? It's going into the page away from us. Then if we think about it that way, then we stick our thumb in the direction of the current. So now our thumb is going into the page. Then do you agree that the current is going to curl around and it's going to go clockwise? Whereas if the current is coming towards us, you can point the thumb towards you, then in fact, the fingers are going to curl around this way, okay? So they're going to curl around that way. So that's how we can work out the direction of the magnetic field around straight conductors. Okay, now we need to talk about how the electric field interact if the currents are parallel conductors, okay? In other words, what will happen if there are two conductors that are held parallel to each other, and how will they interact with each other, okay? So the interesting thing about this is that the currents in the same direction will have an attraction between the two wires, and currents in the opposite direction will have repulsion. Let me explain to you why. I'm just going back for a second. What happens is, let's say I draw another one here belonging to this left-hand side. Okay, so this is going like that, like that, like that, like that, and like that, right? And I might as well draw another one here. Okay, right. Then let's pretend that this green one belongs to this dude, and this is his magnetic field lines. Okay, so do you agree that these magnetic field lines, okay, are actually reinforcing each other. So what happens is that if they're traveling in opposite directions, the magnetic field lines actually reinforce each other, and what happens is there is repulsion, and the wires actually push away from each other, okay? Because these guys are reinforcing each other, they actually cause these wires to be pushed away. Okay, wrong way. Okay, so that is what happens. Okay, whereas if you've got wires going in the same direction, then what happens is you'll get a wire, the field line which will come along here, but that'll be in that direction, and this field line will be coming along here, but it'll be in this direction. And check it out, they're in opposite directions. So that is effectively the same as this happening, where this crest is moving in this direction and that trough is moving in that direction. So it ends up that they neutralize each other. Okay, so you end up with a nice empty area. And because of that, these wires are attracted towards each other, so they move towards each other. Okay, so currents in the same direction, there is attraction between the wires, and currents in the opposite direction will experience repulsion. Right, okay, now let's move on. So now let's talk about the direction of the magnetic field about a solenoid. But first most importantly, we need to talk about what is a solenoid. Now, a solenoid is just a coil of wire. That's all it is. You can make it into something fancy by wrapping it around something interesting or whatever, but basically it is just a coil of wire. Okay, now what you'll notice is, if you look at it, what they've done, and they've connected it to a battery. When you connect it to the battery, then when they place magnetic, compasses, little compasses around it, then they will find that there are magnetic fields around it, and they find the direction as usual. But now, if we want to discover which side is going to be the north side and the south side, so basically, do you agree we're making a temporary magnet? This looks like a temporary magnet. Do you agree? Because there's a magnetic field. But now we want to know which is the north side and the south side of this magnet. So the way you do it is you clasp the solenoid again in your right hand. But this time, last time we led with our thumb. We knew which direction the current was going in. It was in the wire, right? So the current was in a straight direction, so therefore we used our thumb. Whereas in this case, what we're doing is we're saying, hang on, the coil is the electricity, okay, is the wire this time. So what we're going to do now is we're going to use our curled fingers, and we're going to curl them in the direction of the conventional current, right? So it's obviously from positive to negative again. Then the thumb is going to point to the north pole of the field, okay, about the solenoid, as you can see from here. Okay, so you take your fingers, you curl them in the direction of the current in the wire, and your thumb will point to the north pole. So let's just talk about environmental impact of overhead electrical cables. Okay, in South Africa, the voltages in overhead power cables and are as high as 765,000 volts. Okay, that K stands for kilovolts. That's 765 kilovolts. Okay, which is 765,000 volts. 765,000 volts. That's a lot of volts, okay? Which means it is very, very, very dangerous. So what's important is to understand that every one of these pylons is earthed, okay? They touch the earth, so they are earthed. So if you want to, you could, but okay, just let me talk to you about this. I don't know if you've ever seen, but people have seen little birds sitting on the wires, and they go, well, why don't the birds get fried? But that's because the birds aren't earthed. So basically, the current doesn't run through the bird, it runs past the bird, okay, and the bird doesn't actually get affected. But if you've traveled a long distance from Cape Town to, I don't know, Mpumalanga or somewhere that way, then you might have seen some monkeys that have been burnt and killed on these power lines. And the reason that they've been killed is because what has happened is they've had 1 foot on the pylon, okay, and 1 foot on the wire. And what happens is they are then earthed, okay? So what happens is they die because they basically get electrocuted, because this foot is earthed to the ground. So now the current, all that 765,000 volts, is going to try and go through this poor monkey. And also you might have seen, so the actual voltage, the 765,000 volts, won't kill us if we just sit on here. But if we touch the ground, it will definitely kill us, okay? Similarly, there's been incidents where people have gone paragliding or hang gliding, no, paragliding or, what is it called? Parachuting, where their cable cords get stuck on the parachute gets stuck on these power lines. Now what's important is if the person is stuck on the power lines, okay, but their parachute isn't touching the ground and they're not touching the ground, they're just hanging here, then life is okay. But if this if they lean down, if this bends, and they end up touching the ground while their parachute is still touching it, they will die. So the best thing for them to do is cut this cord and fall. Even if it means you're breaking a leg, because otherwise you would die. Okay, so that's really the important thing. Okay, now environmental concerns. A lot of people are struggling with these environmental concerns, and some of them haven't actually been proven or even disproven to be a problem. But the point is that people are concerned about it, so we need to take it into consideration. The first thing is that people are worried about the fact that if there is so much voltage going through those wires, then obviously there must be some health hazard to us. I mean, because if it causes a magnetic field, then obviously it's causing a huge magnetic field around those wires, okay? So that is part of the concern. The second thing is animal hazard. I've already mentioned the poor monkeys. Visual impact doesn't look that pretty. I mean, even this photograph, which is a pretty photograph of a sunset type thing, not very pretty. And then obviously, because of the fact that it's quite dangerous, it uses up a lot of land. Okay, so basically all the area around this land will not really be in use. So that is a bit of an issue. But obviously we need the electricity, so we need to work out a way to get the electricity to us without causing so many issues. Right. So now let's talk about electromagnetic induction. So what we've been talking about is the fact that around a wire, okay, you will find a magnetic field, right? So electric current can be generated in a coil by pushing a magnet into the coil. So what someone found out is they said, okay, fine, well, hang on, let's think about this. If we can get a current to cause a magnetic field, can it work the other way? Could we possibly get current using a magnet? And the answer is hell yes, we can. So electric current can be generated in a coil by pushing a magnet into the coil. When it is pulled out of the coil, a current in the opposite direction is then set up. Okay, it's important to note that there's only an induced current while there is movement of the magnet relative to the coil and vice versa. Okay, so I want to show you this quick little video. I just want to make that 0. Okay. So what they've got here is a circular coil made out of copper wire, okay? And here is a galvanometer. Now remember what a galvanometer is. It's basically something that can either measure volts or amps current, okay? So what is happening is that there is no battery being used, okay? But they do have a bar magnet. And you will notice that as the bar magnet is moved in, the current flows one direction, right? So it goes only in one direction, and it's very instantaneous. It only works very briefly as the bar magnet is moved in. Now watch what happens when he pulls it out. It goes in the opposite direction. So the deflection of the galvanometer is in the opposite direction. That means the current is now in the opposite direction. Similarly, if I push the south pole in, then it goes in the opposite direction there, and then if I pull it out, it goes in that direction. Okay, so do you see that if I'm pushing it in the one way, it goes in one direction, and if I'm pushing it in the other way, it goes in the other direction, okay? That is important, okay? So also please note that there's only a current while we are moving. It is no current when we are not moving. So the theory states the current produced by the relative motion of the coil or the magnet is called an induced current and is said to be set up by an induced electromagnetic force. Okay, and you don't have to worry about that too much. So what we are saying is that we can either move the magnet over the coil, or we can move the coil over the magnet. Right, so now, I actually wanted to show you this. Now I wonder where I saved it. Okay, just hold for half a second. I just need to, actually no, it's fine. Sorry. We just have to go onto the interweb for a second. I forgot that I wanted to show you this. As far as I remember, this comes from FET. Let me just see, it should say on the thing. No, it doesn't, but it is FET. Okay, let's go to FET. PhD. Okay, so what this is a website by the University of Colorado, which has different simulations for physics and chemistry. And if you've been watching these lessons quite often, you will see that I use them quite often. They are free to be played with and used. We want physics. They've got tons of simulations. They're very cool. And I want electricity, magnets, and circuits. Okay, and then I want the one with the electromagnet. There it is, new. Yeah, normally with some of them you can download them, and that's not the one I asked for. I didn't ask for John Travolta, I asked for new. There we go. Some of them you can download and play independently, and some of them you have to use on the actual internet, like this one. Okay, right. So what we're doing now is we're looking at Faraday's law, and we needed to talk about this. So what we showed you so far, and I'm not going to worry about the field lines at the moment, watch what happens to the voltage in the light bulb, okay? If I take this magnet and I move it in, do you see that as I move it in, the light bulb goes? Okay, let's start again. So you can see that I'm going to push the magnet in and watch what happens to the voltage in the light bulb. Okay, I'm just pushing it in once. Okay, so you see that the voltage goes this way and the light bulb lights up. If I go back, the voltage goes in the opposite direction and the light bulb goes. Okay, so if I do, every time I do this, I get. Now, think about those very cool light bulbs, I mean not light bulbs, torches that you get where you can shake them and you get electricity. This is effectively what you're doing. When you're shaking them, you're actually shaking the magnet and you're going ding, 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 and it's going through a coil and it's generating electricity. Okay, but what then happens is there's a battery that stores the electricity, so it doesn't shake like this. But that's effectively what we're doing, okay? Now if I swap it, well, look what happens to the direction of the field. It's in the opposite direction, okay? And again, you will see that it goes in opposite directions. Now, another thing that's important is the number of coils. If we push this through, I want you to look at the size of the voltage and the brightness of the light bulb. So if I do this, okay, size of the light bulb, voltage, not so much. Okay, now we go this way and we push in, much brighter, and the voltage is much bigger. There's one other thing I want you to notice. Look how if I go through this fast, look how nice and bright it is and how the voltage changes. Whereas if I go through this slowly, the voltage doesn't increase that much, okay? So the size of the induced potential difference, in other words, the one that we made, induced means made, okay, depends on a couple of things. First, the strength of the field lines, in other words, the strength of the magnet. The bigger the magnet, the stronger the magnet, obviously, the greater the magnetic field, and therefore the greater electric field, okay, obviously. Next, the number of lines cut, in other words, the speed of the magnet. How many lines cut per unit time? In other words, the speed of the magnet. Oh, darn it. How quickly they are cut, sorry, the number of lines that are cut is not the speed of the magnet, but how many coils we've got, and the number of turns of the wire. Okay, so what we're saying is that and just to talk to you about this thing, the fact that, I prefer it this way, the fact that, let's just show you the field lines, okay, so there's the field lines, right? Now, as I'm moving this, okay, do you see that I'm cutting lots of field lines? Okay, let's just make it back to this one. Lots of field lines, right? Lots of field lines. Okay, just show you something else that's interesting. See that even though I'm not going through, because I've got some field lines cutting it, okay, not as many, but I've got these two field lines cutting it, I'm getting some electricity out. Do you see that? Whereas if I'm going through here, check all the field lines that are cutting it. It's 1, 2, 3, 4, 5, 6, 7. Okay, so there's going to be lots of electricity. So that's what they mean. Also, if we go over here, few field lines are being cut. Okay, lots of field lines being cut. Okay, now I'm going to go fast as well. Even when I go fast here, do you notice it never quite gets as bright as if I do it here? So do you understand what I mean by the number of field lines that are cut, the rate at which they are cut? Okay, obviously the stronger the magnet, the greater the number of field lines as well, because the more intensity. Okay, so now, oh, sorry, I forgot something what I was doing. If you look at this, we want to show you something is, look at the direction of the voltage as I move in. See, it goes the one way, and as I move out, it goes in the opposite direction. In, out, in, out. So we're getting alternating current. Do you understand that? The current's going the one direction and then the other direction. So somebody actually explained that, and they said, as the North Pole moves into the coil, Faraday actually explained it, the North Pole is going to act this end of the basic. Okay, this is the way it works. Okay, the coil tries to protect itself, so it's going to try and prevent the magnet. The way it works is, you think of it this way, as the coil is trying to prevent the magnet from getting in initially. Okay, so what happens is that if the magnet is coming in, and the magnet now is the North Pole and this is the South Pole, and it's trying to get in, then what's going to happen is this is going to act like a North Pole. The coil is going to act like a North Pole to try and repel the magnet from going in. But now once it's in, as you try and pull the North Pole out, it's going, Hawkeye, you can't leave. Okay, so therefore, so it's just like a guard. Okay, therefore it's going to change to the South Pole, which is why it changes direction. So as the North Pole moves into the coil, a North Pole is formed at the near end of the coil. This coil acts like a North Pole. Okay, and it tries to basically oppose the incoming North Pole. So it sets up an induced current in that direction. Whereas, as the South Pole is moved out of the coil, the South Pole is formed. Okay, so basically what happens is it's trying to prevent a change. Okay, and it's all based on effectively the chaos theory, which is saying that entropy and chaos, which basically says that the science doesn't like change. Okay, so it tries to prevent change the whole time. Right, so that's all you guys need to know about electromagnetism officially in grade 11. Your teachers might teach you more than that, but that's all you officially need to know in grade 11. Okay. So now, and it's not a bad thing if they do try and teach you, if they do teach you more than that in grade 11, because you've got to know it for grade 12 anyway, so it's not a bad thing at all. Right, so now let's carry on and let's talk about electricity and circuits and Ohm's law. And I may seem to be going a bit fast in these sections, but we're kind of running out of time. We finish these lessons next week, Friday. And I was kind of hoping to do some revision with you guys, but at the moment it doesn't look like that's going to happen because we're still trying to finish the curriculum. So we're working on it. Okay. Right. So let's carry on. It says, Ohm's law states, for a resistor at a constant temperature, the ratio V over I is constant. And this ratio is called resistance. That is effectively and officially Ohm's law. Okay, so if you guys are asked to state Ohm's law, this is what you would state. Right. Now, what that means is that at a constant temperature, the resistance of the conductor is constant. the resistance of the conductor is constant, and it's independent of the voltage applied across it or the current applied across it, okay? So it doesn't matter how much voltage you're putting across it or how much current you're putting across it, it's going to have that amount of current, okay, and voltage. Understand? Right, so now non-ohmic conductor, well, obviously ohmic conductors obey Ohm's law, okay? And examples are your circuit resistors and your nichrome wire. Non-ohmic resistors do not obey Ohm's law. So in non-ohmic conductors, their resistance changes as the temperature changes. For example, light bulbs, and we actually use this. Now listen, I'm not talking about the new energy-saving light bulbs that don't have a little tungsten filament. The tungsten filament is this bit over here. That funny little wire thing is made from tungsten. And tungsten has a very, 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 very high resistance, okay? Incredibly high resistance. So what happens is that it gets very hot as electricity goes through it. And because of that, it gets bright. So the heat and the brightness of it is actually a byproduct of the fact that it has got electricity going through it, okay? In other words, the main thing that we get out of a light bulb is heat. Okay, these type of light bulbs. That's why they get so hot. The light is a byproduct. Okay, it is not what we were, not what it is. Basically what happened was that someone put this into a thing, it got really hot, they realized that, oh wait, if it gets really hot, it might give off some light, and that's exactly what it did. Okay, so these graphs are for an ohmic versus a non-ohmic resistor. Okay, so as you will notice, okay, it is pretty obvious that an ohmic resistor follows Ohm's law. Ohm's law says that resistance is equal to V over I. So therefore, it should be a straight line, okay? A straight line graph. Yeah. Okay, this is a non-ohmic conductor, which means that the current is going to decrease as the voltage increases, okay, at one point. Okay, it's not going to be a straight line graph. And for that reason, we call it non-ohmic. Okay, the resistance gets more and more and more, basically. Right, now we need to talk about EMF and potential difference and the difference between the two. Okay, so I think the best thing is, remember that these are supposed to be revision lessons. So you guys should know most of this stuff already, okay? But you need to understand that the EMF is the maximum voltage a cell can supply circuits. That's interesting. I suppose so. A circuit, okay? Maximum voltage a cell can supply a circuit. Okay, I don't know what I was thinking when I said circus. There isn't even one in town, so I don't know where I was going with that. Okay, so it's a maximum voltage a cell can supply a circuit. Okay, so whereas potential difference is the voltage that is actually supplied to the circuit. Actually supplied, okay? So it's important that you know the difference, okay? The difference is called the lost volts, okay? And that is the EMF, which is the maximum voltage, minus potential difference, is called the lost volts. And the lost volts are basically due to the internal resistance of the battery, okay? The internal resistance. And the internal resistance is caused by the current flowing through the cell and the cell trying to get the electrons and electricity through the battery. So let us talk about load versus internal resistance. Now, load, which isn't actually used that often, we don't actually use the word load very often, but I have to go through it with you because it is in the curriculum and it's a very important word if you don't know it. So load is effectively the external resistance in the circuit. So everything outside the battery is called the load. So if they say, what is the load of the circuit? Or if they say, calculate the load of the circuit, then they're effectively asking you to calculate the external resistance of the circuit. Okay, now we are looking for the, so therefore it's represented obviously by R because it's and it's measured in ohms because it's an external. And the V load is obviously IR. The internal resistance is represented by little r. So the internal is the volts, which are this is the last volts. This is the last volts. And that is I, the current in the circuit, times by R. Therefore, your EMF is equal to your V load plus your last volts. Okay. So right, so the best way to do this is actually to do an example. So let's work through this example. It says, determine the internal resistance of a battery that has an EMF of 12 volts. So let's write that down. The EMF is 12 volts. It has a potential difference across its terminals of 10 volts. So the V is 10 volts. When a current of 4 amps, I is 4 amps. And it says flowing through it. And it wants the internal resistance, which is R. Okay, so that's actually a really easy question. They really weren't pushing us too much. So we're solving for little r. So we can substitute in. We've got 12 is equal to 10 plus 4r. So degree at 2 is 4r. So r is going to be 0.5 ohms. There we go. Nice and easy, hey? Right, so now again, I am doing this hoping that since this is supposed to be revision, that you guys will cruise through these examples with me now. Okay, so let's get going. It says, consider the following, Consider the following circuit diagram drawn below and answer the questions using the information supplied. So let's have a look at it. Here is 1, 2, 3 cells. There are 3 cells. Okay. There's a voltmeter across it. There's an ammeter over here. A resistance 1 with an ammeter 1. Resistance 2 with ammeter 2. Resistance 3 with voltmeter 2. They say voltmeter 1 is measuring 6 volts. It says V2 is 4 volts. And ammeter A1 is 0.5 amps. And A2 is 1.5 amps. Okay, so do you agree this is actually quite an easy question because to even to start with, for the simple reason that nowhere do they mention internal resistance, so we don't even have to worry about that, okay? So life is pretty cool at the moment. Now, it says, calculate the reading on R1. So we want the reading on R1. Okay, so do you agree that this voltmeter reading is reading the total volts of the volts to the circuit, okay? So the total volts to the circuit is 6 volts. This voltmeter reading is 4 volts, which means that if I had to put an imaginary voltmeter across here, do you agree that it would read 2 volts? Okay, because this voltmeter is measuring the total volts of the circuit. And grade 11s, I just realized that we're out of time. So we will start again on this on Tuesday. We will carry on with this on Tuesday. Have a great day. Cheers.